Hi, welcome. In this video, we are going to talk about instrumentation amplifier. So we are going to do some experiments with instrumentation amplifier. Okay, this is at a first glance is a very complicated circuit. So I am just showing you the circuit that you will see in your manual, in your lab manual. So this is a very complicated circuit. It has 1, 2, 3 op amps. One op amp is so difficult, and 3 op amps is like an hell. It's very difficult at a first glance. Okay, and I mean, I always wonder how could someone come up with such a complicated circuit, and someone says, yeah, use this complicated circuit and this will act as an amplifier. I don't know, they are genius who actually find out these circuits. To me, they are really genius. Okay, in this video we are not going to motivate the synthesis of this circuit. Okay, so any circuit can be, we can talk about any circuit from two perspectives. One is the synthesis of the circuit, that is how to come up with such a complicated circuit. It's a nightmare to me. And the second possible perspective to look at a circuit is, given the circuit, analyze the circuit. Okay, so given the circuit, suppose someone has already told me that this is a circuit. Now let us analyze how the output is related to the inputs. So that is comparatively a simpler thing to do. And we being at this point being the beginners, we will look at this circuit from an analyst's perspective. Okay, and in our theory course later we will try to motivate how this complicated circuit is conceived, how one can think of such a complicated circuit in their dreams. I don't know, but here we will consider this circuit from an analyst's perspective. That is, this circuit is given to us, and we will think, okay, if two inputs are given at these two input points, how the output will behave. That will be our approach in this video. Okay, so let us begin our discussion. I will first mention a few facts that you can remember. That instrumentation amplifier is a difference or amplifier. Okay, what does this mean? This means it has two inputs and one output. The output is a function of, or is proportional to, the difference between two inputs. Okay, if the two inputs are, let the inputs be equal to V1 and V2, two voltages, then the output will be VO is some constant times V1 minus V2. So the difference between the two inputs is multiplied or amplified by a factor K, and that becomes our output. Okay, so this is what a difference amplifier is. Now, I believe you already have studied op-amps and you already have studied basic circuits like inverting, non-inverting and difference amplifiers with an op-amp. So let me just recap one circuit. Difference amplifier with an op-amp. Let me recap this. Okay, with an op-amp, or you can say with one op-amp, only one op-amp. So that circuit looks like this. This is my op-amp. It has two inputs, minus, plus, one output, and there will be a potential divider connected here, and we'll have one input here, call it V1. There will be one more input here, call it V2, and there is a feedback from output. Let me call these resistances as R1, R2. This resistance is taken to be same as R1 and this resistance is taken to be same as R2. This is the output VO. This circuit I'm not going to analyze now. You can find the analysis in other videos. Here the output VO becomes equal to R2 by R1 times V1 minus V2. This is true for this circuit. Okay, so this is also a difference amplifier, and that's why its name is difference amplifier. But this difference amplifier is made up with one op-amp. Okay, so there is only one op-amp which amplifies the difference between the two voltages V1 and V2. An instrumentation amplifier, on the other hand, the instrumentation amplifier, as I already have said, is a difference amplifier, but it is a two-stage amplifier. Okay, so the difference between two voltage is amplified twice. Maybe in some part of the circuit it is amplified by 10 times, and then that voltage is fed to another amplifier which amplifies that voltage, that difference, again by 10 times, so that finally we have a 100 times amplification. So that's what is known as two-stage amplifier. It's like this. So this may be one amplifier, stage 1, and then stage 2. It will have two inputs definitely. So it will take the difference between these two inputs, V1 and V2, that will be multiplied by, say, a factor of 10. Here we will have 10 times the voltage, and then here we will have again 10 times that voltage. So finally this voltage will be 100 times V1 minus V2. That's what a two-stage amplifier is. Okay, so our instrumentation amplifier is going to be a two-stage amplifier. Now let me just for a while look at this complicated circuit which you find in your manual, and let me just tell you that these two are the inputs. Okay, maybe this is V1, this is V2, this is the output, and it is amplified twice. Here this is one stage. Okay, so this difference is amplified and comes out through these two terminals, and this is again fed to the second stage, and finally the output comes here. So this amplifies this difference by some factor, call it A1, then this amplifies by some factor, call it A2. So finally the amplification will be A1 times A2. Now let us understand these two circuits one by one. Okay, we will draw these two stages one by one and we will analyze them. So let's look at stage 1. How does it look like? It looks like this. There are two op amps in stage 1 like this, side by side. It has two inputs. Each of them has two inputs. And this, okay, let me first draw this circuit. Okay, so this is like a potential divider with three resistances. From, let me call this R2. These two resistances are same, R1 and R1. Okay, from here I have the feedback, from here I have a feedback, and here from these two terminals I will have two inputs, call it V1 and V2. Okay, and these two will be two outputs, call it VO1 and VO2. So this is how this stage 1 looks like. It has two inputs and two outputs. Okay, how to remember this circuit? I'll now tell you how to remember this circuit. How to remember? This circuit, this part of the circuit. Okay, you just need to know a non-inverting amplifier. Okay, let me do it here. So how does a non-inverting amplifier looks like? This is a non-inverting amplifier I'm going to draw. It has the input coming to the plus terminal and the output, a fraction of the output is fed back to this inverting terminal. Okay, so this is V, if this is VO, a fraction of that, okay, call it R1 and R2. So a fraction, this is a potential divider, so a fraction of this voltage goes back to the non-inverting terminal. Here is the input, here is the output, VO. This is a non-inverting amplifier. Be careful about the plus and minus sign. So I believe this is what you already have studied and this is what you already know. So you can remember this. Now what you do? You do the following. Draw two non-inverting amplifiers like this. So one is here. I'm just copying this circuit. So this is one non-inverting amplifier, feedback in the negative input terminal. This is the input to this amplifier, call it VI. This is the output, call it VO. Okay, so this is one non-inverting amplifier. Now draw another non-inverting amplifier in an opposite, in an opposite inverted direction. So draw that with the minus terminal above and plus terminals below. Okay, like this. So the input will be here definitely, output will be here, okay, and a fraction of the output comes back to this, right? So this is just a mirror image of this. If you just flip it, you get this. This is just a mirror image of a non-inverting amplifier. Okay, now what you do, I mean, you draw them such a way so that this actually should be grounded. This actually should be grounded as here. You draw it in such a way that this grounded point is facing each other. Now you just do this. Sort them. Instead of grounding them, just sort them. Okay, so these two together is now one resistance. I can call it R2. This resistance now says you take similar, identical, because these two you have to take identical copies. So if this is R1, this also has to be R1. Okay, now this is another input. If you call this VI, or you call it VI1, you call this VI2, input 1, input 2. Then you can call this as in output 1, output 2. Okay, so this circuit is just this circuit. So that's how you can remember stage 1. You just need to know this non-inverting amplifier, and you make two copies, one being the mirror image of the other, and join their common this grounded point together, and this becomes together one resistance R2. Okay, so this is, and here to be consistent you can call this as VI1 and VI2, input 1 and input 2. This is stage 1. Okay, now this is how you can remember this circuit. Okay, so this is how you can remember this circuit. Now what we have to do, we have to analyze it or do the maths. That means how these two outputs, how VO1 and VO2 are related to V input 1 and V input 2. So that's what we are going to talk about now. This circuit is given to us. We have said how to remember this, and our approach in this video is the approach of an analyst. That means I'm not going to synthesize this circuit, but given this circuit I'm going to analyze what is going to happen. Okay, that's our approach. And we have also talked about how to remember this circuit. Now let's do the analysis. Okay, let's do it. So this part itself is a non-inverting amplifier. That's how we have drawn it. At least it seems like we have to do more rigorous justification, but okay. Assuming, let me just say now, for now, assuming both op amps in this circuit behaves in a manner similar to non-inverting amplifier, we can say virtual sorting is applicable in this circuit. So this long statement is a very, this is like hiding a lot of details by this assumption. There are a lot of details hidden under this assumption that virtual sorting is true. We'll try to justify that in a while, maybe briefly, but right now we'll make this assumption. If so, then these two terminals will be at the same potential, these two terminals will be at the same potential because of this assumption. Okay, so this will be VI1, this is Vi2, that means this will be Vi2. They are at same point. If so, this point is at Vi1, this point is at Vi2. Right? If so, then the current that flows through it, if I call it I, then I will be equal to Vi1 minus Vi2 divided by R2. If so, then what is the difference between VO1 and VO2? I can write VO1 minus VO2 is equal to I, this current. Note that this current I must flow also here, same current I, because no current can flow through this input terminal of any op-amp. That's what we all know. Okay, and here also no current can go in or go out. So the same current I must flow here. So this current I flows from here to here, same current. So if so, I can write this I multiplied by this total resistance, which will be R1 plus R2 plus R1. That means 2R1 plus R2 is this difference. Now this is equal to what? I put in place of I write Vi1 minus I1 minus I2 whole divided by R2, and this is multiplied by 2R1 plus R2 is this. So the difference between these two output is proportional to the difference between the two inputs multiplied by this factor. R1, 2R1 plus R2 by R2. Okay, now I can have this R2 variable here as well, this R2 variable. Therefore, by changing this R2, I can change the gain of this circuit. Okay, so here you see VO1, let me write it once again, is 2R1 plus R2 by R2 times Vi1 minus Vi2. So if I, or let me write it this way, this is equal to 1, R2 by R2 is 1 plus 2R1 by R2 whole multiplied by Vi1 minus Vi2. So if I increase R2, then this term will reduce, so gain will be reduced. If I decrease R2, gain will be more. So this is a difference amplifier. Okay, with two inputs and two outputs. The difference of the outputs is proportional to the difference of the inputs. Okay, that's very simple, right? So to remember this circuit, just remember a non-inverting amplifier, copy it twice, with one being the mirror image of the other, and then as soon as we make this assumption that these two inputs are at same potential, these two inputs are at same potential, this is now very easy to find the relation between VO1 minus VO2 versus Vi1 minus VO2. It's simple. Okay, now let me digress a bit and try to justify the virtual sorting in this circuit. Okay, because we said that virtual sorting is applicable in this circuit, but in general in all circuits op-amps will not have these two terminals at same potential, or these two terminals. In general it's not true. In this circuit it's true. Let me try to justify that this is true in this circuit. Also a note, this virtual sorting will not be true if you by mistake flip the plus minus terminals. If you by mistake make this minus this plus, or this plus this minus, this virtual sorting will not be true, okay, and in that case this analysis will not be true and your entire circuit will be wrong. So don't make this mistake. So therefore let me just talk about and just justify why this virtual sorting is true in this case. Remember it this way, okay? If I apply, say, a positive voltage here, suppose I apply a positive voltage, this is applied to the positive terminal, and therefore the op-amp output will try to go up. If this output is going up, then this point, the voltage at this point will also go up, and this is connected here. How long will it happen? This output will go up until and unless this point, potential at this point, goes up and becomes equal to this plus voltage. Okay, so this remember, we know that if I call this Vp, if I call this Vn, P for positive, N for negative, this is Vn. Okay, we know for op amp Vo is positive if Vp greater than Vn, and Vo is negative if Vp less than Vn. So just you can remember it this way. Suppose at any instant Vn is 0. I'm repeating. Okay. Suppose at any instant Vn is 0. This is at 0 potential, and I give a positive potential here at Vp. Then output will try to go up, which will cause this point to also go up, and at some instant this will become equal to this, and the op amp will be happy when these two inputs are at same potential. Okay, so you may remember this in that way, that if this is positive, output goes positive, this also goes high, and it makes Vn also positive, and therefore these two comes at the same potential, and that's why the virtual sorting is true. These two are at same potential. So that's how you can remember the fact that virtual sorting is true here. Okay, let me now make a wrong circuit for you by intentionally flipping this plus minus sign. Okay, so I will intentionally draw the same circuit. First I draw the same circuit. Okay, and I have feedback here and I have a feedback here. Let me keep this as correct, minus plus. So this is one input, and here I have another input, and intentionally I make it wrong. I make it minus, I make it plus. This is wrong. Okay, this is absolutely wrong, but let me justify that this is wrong. What will happen in this case? Suppose you apply a positive voltage here. Okay, you start your thought assuming that initially this was at 0. Now this is plus, and this is what? This is Vn, this is Vp. Now what happens? Vn is greater than Vp. Okay, Vn is greater than Vp, which will cause this output to go down. This output will go down towards the negative value, causing this also to go down. So this point will also go down, and therefore this voltage will further be reduced. This will be negative now. Okay, and if this is negative, this is positive, that means Vn is still greater than Vp. Output will further go down. this point will further go down, this will be further negative, and this process will continue until and unless this point goes to saturation. This will go to minus V saturation or minus VCC. Maximum, if this is my minus VCC and this is my plus VCC, the power supply, this point will go to the saturation value, and therefore this point will, now if this is minus V saturation, it's highly negative, this will also be negative, it's very much negative, and so therefore this point will be negative, whereas this is at positive. I have given a positive supply, so this is given, this is where I start my analysis from, and I see if positive supply is given here, this point becomes negative. Okay, therefore these two are not at same potential. Virtual sorting is not true. So you cannot make this mistake, minus plus. Here as well you do the same analysis. Okay, this is the correct circuit. So here again, if you give a positive supply, positive is given to positive terminal, which will cause this output to go up, causing this point to the potential here to go up, and so this potential will go up and be equal to this plus value, and the op amp will be happy at that point. If you make it the other way, if you make this plus, this minus, then the op amp will go to saturation. Think about it cautiously. So this is the correct circuit. If you make this mistake, either here or in both cases, you make it like this, then this is wrong. This is absolutely wrong. Okay, be careful about that. Be careful about the plus minus sign. Okay, good. So what we have seen, let me recap. Okay, recap. I'm just recapping what we have talked about so far. We are talking about the stage 1 of our two-stage amplifier. We have talked about how to remember this stage 1. You just have to remember this non-inverting amplifier. Draw it twice, once and twice, by flipping it as a mirror image. Join this grounded point of these two amplifiers together. That's how you remember this circuit. And while doing the analysis, this we know here these 2 points will be at same potential. These 2 points will be at same potential. So if this is VI1, this will be VI1, which means this will be VI1. Similarly, if this is VI2, this will be VI2, which means this will be VI2. So you can compute this current, and therefore you can compute the difference between VO and VO2, which is very simple here. Now you have to be careful about this plus minus. Here as well plus minus. If this plus minus is reversed, this assumption of virtual sorting will not be true. This derivation will be wrong. So think about it, like what happens if you give a small positive supply here, the output goes up and it makes the other terminal equal to this. But if you make, or you can also think you give a slight negative voltage. Okay, suppose you give a slight negative voltage. This, now start your assumption by saying that at any instant this is 0. You will give a small negative voltage. This plus terminal is at negative voltage, which will cause the output to go down. Okay, therefore this point will also go down in potential, and this 0 potential will become negative, and they will be equal. To do this analysis, you just need to remember this. This is the fundamental rule for op amp. Output depends on which input is higher. If VP is higher, output is positive. If Vn is higher, output is negative. That's all you need to know. Okay, so this is all about stage 1 of our complicated circuit. Stage 1. Now let's talk about stage 2. So let's talk about stage 2. Stage 2 is very simple. Stage 2 is nothing but a difference amplifier. Let me show you. So we started our discussion in this video with this circuit, right? With this circuit, which is just a difference amplifier, which I have assumed that you have already studied. Now in this circuit, you see that this part is just same as this part. Okay, here you have R1, R1. These R1, R1s are this. This R2 is this R2. Okay, this feedback. And this is here. So this is just a difference amplifier. So what will this do? The final output here will be, let me look at this equation. Final output will be R2 by R1 times the difference between these two. Okay, now here this is my stage 1, right? This is my stage 1. This is stage 1. So I have VI1, VI2, and this I'm calling as VO1 and VO2. Okay. Okay. Let me, instead of calling this R1, let me call it R3, because I have already used R1 for this here. And let me call this, yeah, it's already so let me just call it R4. Okay. So now it's very simple. Look at the equation of a difference amplifier, and let me do it here. Okay, so let me just do it here. So according to this notation, I call this as R3, this also as R3, this as R4, this as R4. Therefore I better write it as this VO is equal to R4 by R3, V, these two differences, V1 minus V2. Now what is V1? V1 is, according to this, V1 is VO2. According to this notation, this is actually VO2, not V1. This is, according to that notation, is VO2, and this is actually VO1. 1 and 2 is swapped here, okay, doesn't matter. So here I can write this is equal to R4, R3, and this multiplied by VO2 minus VO1. And then we have seen here for stage 1 that VO1 minus VO2 is this. Okay, so let me just use this equation here. Therefore it becomes VO is equal to R4 by R3 from here, and here instead of VO2 minus VO1, I have to take a minus, so I take the minus out here, and here I write 1 plus 2R1 by R2 VI1 minus VI2. Okay, as simple as that. So that's the equation relating this output versus these two inputs. So it is very simple. Let me maybe for a final revision, let me do it very quickly in front of you. Okay, so let me do a very quick recap in 2-3 minutes. So difference amplifier, instrumentation amplifier is a two-stage amplifier. The first stage has 2 op amps. Draw 2 op amps as 2 non-inverting amplifiers. So the input comes at the plus terminal, and from here we have a potential divider, and a fraction of the output goes to the input, minus input, okay, and I have to draw the mirror image of it, okay. So I have minus here, plus down, this is the another input, and here I need this potential divider, that means two resistances, and from here I feed it back, okay. Be careful about plus minus here, and these two terminals I join together. And if I call it VI1, if I call it VI2, it's very simple. The virtual sorting is true, so this will be VI1, this is connected directly here, this will be VI1, this is VI2, virtual sorting says this will be VI2, that means this point will be VI2. Now I'm calling these two resistance together as R2, this as R1, and this as R1. So the current will be, let me call it I, very quickly, I will be VI1 minus VI2 divided by R2. Do this with me. So this will be this current, and if I call this point as VO1 and VO2, okay, then VO1 minus VO2 is I times this total resistance, which is R1 plus R2 plus R1. So this will become, in place of I write VI1 minus VI2 by R2. Here I write 2R1 plus R2. This is stage 1. Now I take the output from stage 1 here. So this is stage 1. I put it in a box. And stage 2 is just a difference amplifier with a single op amp. So it will have two inputs, minus, plus. Okay, I need to have a potential divider here and a feedback. These two will be the two inputs of this difference amplifier, and we take these two resistances, same R3, R3, these two same R4, R4. This is the final output, call it VO. Now join this to this and this to this. So this output goes as the input to this. This is stage 2. Okay, and here VO is how much? Here VO is R4 by R3. This potential near this plus terminal, which is VO2 minus VO1. And here if I put the value R4 by R3 multiplied by this 2R1 plus R2 by R2. I have to have a minus because here this is 2 minus 1, but here it's 1 minus 2, so I put a minus and hold. Okay, that's as simple as that. So this is the gain. This is the final gain of this amplifier. Now let me just talk about a few new things. Okay, some terminologies, some very important terminologies that you must remember this point onward if you are not already familiar with. If I have an amplifier, okay, this is an amplifier which has two inputs and one output, like our instrumentation amplifier. So I'm drawing the entire circuit as a black box or a white box in this case, and it has two inputs, 1 and 2, and VO is the output. And if it happens that the output is some linear function of V1 and V2, if it is that VO depends on V1 and V2 in this way, that AV1 plus BV2, some linear function. Okay, so in case of instrumentation amplifier, instrumentation amplifier, we know VO is equal to actually some factor times V1 times minus V2 or V2 minus V1, it doesn't matter, K can have the sign absorbed in it. So in case of instrumentation amplifier, B will be equal to minus A, or if I just call it A. So this is a special case. In case of instrumentation amplifier, we know that VO is some amplification factor times V1 minus V2. So if I am using this more general form, then B has to be minus A for this special case. But in general, if it happens that this amplifier has its output which depends linearly on these two inputs, like this, okay, then we can define some terms like this. So in this case, if it happens, I don't know whether it will happen always or not, but if it happens, then I can rewrite this as let me write it as like this, maybe V1 plus V2 by 2 and times some call it Kc plus V1 minus V2 times Kd. I can reorganize this A and B and write this in this way. Okay. If you don't believe, let me just do it. So if I just expand this, you see that then I'll have, with V1 I'll have Kc by 2 plus Kd times V1, and with V2 I will have Kc by 2 minus Kd V2. Now if I just call this as A and this as B, then this is, or you can also from this you can write that Kc is, or Kc by 2 will be A plus B by 2, and Kd will be this A minus B. So you can just choose these values like this, choose Kc equal to this and Kd equal to this, and then you can write it in this way. So essentially we want to write the output as a linear function of the average input and the difference input. That's what we wanted. So see that this is V1 plus V2 by 2 is the average input, and V1 minus V2, this is the difference input. Okay, so we can write this, and we can also sometimes denote this with a symbol. This is called this has a name. This is called VC, or common mode voltage. Common here means average. What is common between V1 and V2? It's the average value of, I don't know why it's called common mode. It's like average mode. Okay, average mode, it's the common mode voltage. And this VD is the this is obvious, difference voltage or difference mode voltage, whatever you like to call it. Okay, so we have written VO as this Kc. Now you possibly already have guessed what Kc means, is some common mode gain, and this is Vc plus Kd Vd. So we wanted to write the output as a linear function of the average value and the difference. Okay, average times average gain or common mode gain plus the difference times the differential gain, KD. Okay, now this is true when if we have an amplifier for which the output is some linear function of the two inputs like this, then we can write it this way. And now if the amplifier is a difference amplifier, which means it's the task of the this amplifier is to amplify only the difference and should not bother about the average. So if I give 5 volt and 6 volt, the output should be same as when I give 10 volt and 11 volt or 100 volt and 101 volt. The output should only depend on the difference. For example, like the instrumentation amplifier which we have talked about. In this derivation, you see the output depends only on the difference of the two inputs. And in this case, we also have said that, okay, if it is an instrumentation amplifier or if it is a difference amplifier, instrumentation or difference amplifier, ideally, then B should be minus A. And if so, here you see B is minus A means Kc is A minus A by 2 will be 0 and this will be non-zero. Kd will be 2A. Okay, so this term will vanish. So VO will be ideally Kc equal to 0 Vc plus Kd Vd. This is non-zero, or Kd times V1 minus V2. This is what ideally should happen, and we call this factor as common mode gain. This terminology you remember, common mode gain, and this is common mode voltage. Kc is common mode gain. Let me write common mode gain. This is differential gain. Okay, essentially how much is the difference amplified is differential gain, how much is the average value amplified is the common mode gain. And for an ideal difference amplifier, as we already have said, for ideal difference or differential amplifier, Kc should be 0, Kd non-zero. And therefore, if we have a difference amplifier, we can measure the goodness of a difference amplifier maybe by this factor, Kd by Kc. Okay, higher the Kd is and lower the Kc is. So if Kd is high and Kc is low, so then this factor Kd by Kc is high. That means good. The difference amplifier is really a good difference amplifier. It doesn't bother about the average value. Okay, cool. And this we will give a name. This factor Kd by Kc is called common mode rejection ratio. As if this amplifier, a good difference amplifier, is supposed to reject the common mode voltage, average voltage, and only bother about the differential voltage. So how much is it rejecting the common mode voltage is found from this ratio of Kd and Kc. This is called common mode rejection ratio or CMRR. Sometimes this is, not sometimes, often, many a times, this is represented in decibels. How? So it's simple. If you, so the output common mode voltage will be equal to how much? It's Kc times Vc, okay, and output difference mode voltage, that depends on, so now if so, output power, that will be proportional to Kc square Vc square, and output diff, in short, power will be Kd square Vc square, sorry, Vd square. Okay, so therefore output power by output diff power will be this Kc square by Kd square multiplied by Vc square by Vd square. Now this is equal to what? Let me write this factor, Kc by Kd whole square, and this is what? This is nothing but input power by input diff power. Okay, so as if this, so this is, so in input, this common mode power by differential mode power is amplified by this factor. Okay, yeah, is amplified by this factor. So this is the amplification in terms of powers. Now this ratio, I mean this number, we can also represent it in log domain. We can just take up log of this, take log, so what we will have, log of this factor Kc by Kd whole square, and this we call as in Bell. And if we take 10 times of this, that will be in decibel square, and this square can be brought out, so this becomes 20 log Kc by Kd. Okay, this is called the CMRR in decibel. So this is a measure of, goodness of a difference amplifier. Now let us come back to our circuit of this two-stage instrumentation amplifier and ask how good it is as a difference amplifier. Let us now ask this question. As we have seen in this equation, according to, let me call this star, according to star, this is a perfect difference amplifier. Okay, but in practice it won't be. Note, but in practice when we make this circuit, it won't be perfect. Why? There can be many reasons, I don't know, but I am aware of 2 reasons at least. Reason number 1, so in this circuit, in our analysis we have assumed what? This resistance is equal to this resistance is equal to this resistance, here this is equal to this. So we assume that these resistances are identical. But in practice they may not be. Resistances or resistance pairs may not be identical. This is one reason, one possible reason. Okay, and I leave it to you in this video as an exercise, or you do it in your discussion section in your report if you like. Take these values as being different, R1 prime, R1 double prime, R3 prime, R3 double prime, R4 prime, R4 double prime. Discussion, take different values of resistances and find VO as a function of V1 or VI1 and VI2. You can do it, right? All you have to do that right now, in place of having this R1, you put a different symbol, here a different symbol, and do the same analysis. This I keep you as an exercise. And then you will find that there will be some other term here which depends on the average value of VI1 and VI2. Do it as an exercise, small exercise. It should be able to do it, or we will do it later in a later video. This is one reason. Another possible reason, number 2, is this actually is going to be a slightly bit advanced topic, but you will also need it for your other experiments too, but let's talk about it. Okay, an op-amp, let us recall the functional behavior of an op-amp. It has 2 inputs, call it plus, minus, call it VP, VN, VO. Then we know the static characteristic of an op-amp should look like if this axis is Vp minus Vn, that is the difference between the 2 inputs. We know if when Vp minus Vn is positive, output is positive, and otherwise it's negative. Okay, this is ideal static characteristic. But practical static characteristic sometimes deviate from this in this way, like the pattern is like this. So this is this line, so this is VO, this is VO, this is again Vp minus Vn. Okay, so this there is a gap of this transition from the VO axis. It happens due to internal circuitry, which honestly I do not know why, but it happens. Okay, so if so, what will happen? But generally this gap is very small. This gap is very small. This offset voltage, this is called an offset voltage, input offset voltage better. Okay, so this input offset voltage is generally at max few millivolt, of the order of millivolt, and if the op amp is good, then it's only few microvolt. For higher quality op amp, it's only few microvolts, or otherwise it's only few millivolts. Okay, so how people tackle this situation? Okay, so here we see that in this, if Vp is, so let me call this this gap, say if this gap is 1 millivolt, for example. So then we see, according to this characteristic, okay, if Vp minus Vn is greater than this, let me call this just offset, not one, let me call it V input offset, Vi or V, okay, let me call it V off. Okay, if this is greater than V off, then Vo positive, else if Vp minus Vn is less than V off, then Vo is negative. Now what I can do, I do this, I write the same thing as Vp minus V off, from here I bring it here, minus Vn, if this is 0, then Vo positive, and if Vp minus V off minus Vn, if this is negative, then output is negative. Okay, now this fact is modeled as follows. We think that if this is my op amp, plus minus, we think that there is a small voltage source called V off, and here is this input terminal Vp. So there is a small voltage source between the input Vp and this plus and this op amp. Okay, and the terminals are for this is plus and minus in this case. Okay, and here is the Vn. We can think of in this way, and this is the output Vo, and this part behaves like an ideal op amp. This part behaves like an ideal op amp. Okay, and but this voltage source is an integral part of this op amp, so you cannot get rid of it, you cannot remove it. Let me then call this point as Vp prime. Okay, this is Vp prime, I'm calling this point. Then now this behaves like an ideal op amp, so we can write that simply speaking, Vo is equal to sine of this thing Vp. I mean, like here, as if we can also have written, okay, that's not, let's do it here. So Vp prime minus Vn. If this voltage is positive, maybe multiplied by some factor. Okay, but I just want to write it in short. That's otherwise I could have written it in this form with if-else statements, just like this. Okay, so Vo is positive when this point is higher, at a higher potential than this point, Vp prime greater than Vn. Okay, because this part is an ideal op amp. Now VP, true VP is here, this is VP prime, so here I can just write VP, this is VP, and then minus VP minus V of, minus V of, minus Vn. I can take this into a bracket without a problem. So this you see is same as this. So these two together is same as, right, VO being sine of this VP minus V of minus Vn. Okay, so this is same as this. So this can be modeled with a voltage source which you cannot get rid of, but it's connected to the input terminal. Let me just tell once more that this is a bit advanced topic. I mean, the thing that I'm discussing in this page is a bit advanced, but it's not difficult to understand if you like, or you can skip. Now, actually, this modeling could also be done this way. You see, I take the op amp, and instead of having this V of here, I take a V of here, but this time with the other direction of polarity. This is minus, this is plus. This is V of, this is Vn, and Vp is here. And this point I'll call Vn prime. This is Vp. Okay, this part is an ideal op amp, so we can write Vo is sine of Vp minus Vn prime. Okay, and now this is same as Vp minus, what is Vn prime? Vn prime is Vn plus V of, Vn plus V of. So let me take this bracket out, then you'll see this is the same, Vn minus V of. So you can model this fact, model the fact that the static characteristic of a practical op amp is not like this but like this. This is an ideal op amp, this is a practical op amp which has an offset in static characteristic here. This can be modeled by this, an additional source in the input terminal, either in Vp or in Vn. You can model it accordingly. I mean, both are equivalent, both are equivalent. So this way one can model this. Okay, cool. Now a little thought will reveal that if these op amps are not ideal, if they have these offset voltages here, etc., then even if you apply same voltage V1 and V2, I mean because of these offset voltages and they not being possibly equal or etc., you'll still have some voltage here, although these two voltages are equal. When these two voltages are equal, they should also be same in an ideal scenario, but they may not be same because of these two things. And then here also you may have something, and then you may still have some output even when these two are same. So this is reason 2 why we can have a common mode gain although the two inputs are same. So two possible reasons are, number 1, these resistances, these two may not be same, or these two may not be same exactly, or these two may not be same exactly, or reason number 2 is that because of this offset voltages, these op amps might have their static characteristics which looks like this. Maybe this one looks like this. So, and this offset voltage can either be plus or can be minus. This can be positive, negative. That varies. We cannot ascertain a priori. Even if you take two op amps purchased from the same place, they can have different offset voltages. This can cause some common mode gain. And I leave it as an exercise only for the interested students, not for all of you. If you are bored, absolutely fine. That you take this offset voltages into account, think if they are not equal, and find the output voltage in terms of this offset voltages and this input voltages as well. You will see, let's see whether you can find that there is a common mode gain or not. Okay. Now, in continuation to this topic, let me tell you a remedy how to get rid of these offset voltages. Generally, op amps, they have this we get this with the 2 input and this with the output, and we know it also has 2 power supplies. I do not remember the pin number of this, but other than that, it will also have 2 pins which are called offset null. Other than all this, it will have also 2 pins which are called offset null. And what you can do, you can connect something like a 10 kilo potentiometer, 10 kilo ohm potentiometer, and so generally we give, say, a plus 12 volt supply. Here we give minus 12 volt supply here. Connect this potentiometer here and connect the variable terminal of this potentiometer to this minus 12 volt supply. And you can vary the position of this potentiometer. By varying this, okay, it is possible to nullify the effect of any here or here, any input offset voltages. So this arrangement is generally kept in op amps. These 2 terminals are called offset null terminals. I do not remember the pin number. You can find it on the web or anywhere else in books. So this arrangement is provided to get rid of these offset terminals. What you can do, you do this following experiment. You connect the op amp so that it has these 2 power supplies. Give these 2 power supplies, plus 12, minus 12 volt. Connect this potentiometer. Have this variable pot. Now you short circuit these 2 terminals, inverting and non-inverting amplifiers inputs, and then the output should be 0. VO should be 0. If it is not 0, then you adjust this pot this way or that way until this becomes 0. So this adjustment is provided. So this is offset null adjustment. So you can do this. Okay, so now in this circuit, this is your 2-stage instrumentation amplifier which has 3 op amps. Ideally, if I now give same input to both this, or if I just short circuit this, then the output should be equal to 0. Okay, now what you can do, so all these op amps have this offset null things. You can use all of them. You can adjust this. You can adjust this offset null so that this becomes 0. Now the obvious question that must be coming at your mind in this point, which one to be adjusted? There are three of them. Okay, this I leave as an exercise. Once again, you can put this in your discussion, what you may like to do. You know, you can maybe you just first short circuit these two, adjust this one until this becomes 0, then you may short circuit these two, adjust this one until this becomes 0. Now then after that, or maybe you then individually do it, short circuit this one, adjust this to make that 0. But actually maybe you can also take care about the non-equality of these resistances by adjusting these offset voltages, etc. So this becomes a bit more involved. I mean, think about it. I'll leave it as a thought exercise for you. Think, how will you and propose a scheme, how will you adjust these things so that can you take care of all these offset voltages in 3 op amps? Can you also take care about this non-equality of these resistances with this facility? Think, I mean, think about it. I just leave it as an exercise to you. But the more important thing I'm going to talk about is this. Suppose you do this, that you short circuit these two terminals and adjust all these offset nulls so that the VO becomes 0. So here maybe that at this instant you give 0 here, and the you adjust all this so that the output becomes 0. So what you do? Maybe that suppose you do this. Suppose you do this. Make V1 one input equal to 0, V2 another equal to 0, and adjust offsets to make VO output equal to 0. Suppose you do this. Is there a guarantee that when V1 is equal to say 5 volt, V2 is equal to 5 volt, so these two are still equal, is there a guarantee that when this is equal to this and this is equal to this, VO will be 0? You have adjusted the output to be 0 when the inputs are 0, 0. Okay? The output should be 0 because it's a differential amplifier, So when the inputs are equal, the output should be 0. And you have done this when the two inputs are 0. Suppose, is there a guarantee that when the two inputs are equal but not 0 but 5 volt, the output will still be 0? Think. Thought exercise. Think about it. I don't know the answer to it. So what you have to do in your experiment in lab, you have to find it out by experiment. Okay? Find it out by experiment. So suppose you do this adjustment when the two inputs are at 0. Now you check whether the output is still 0 when the two inputs are at 5 volt. If not, if VO not equal to 0, then find common mode gain Kc, which will be what? VO, which is not 0, divided by this V1 plus V2 by 2, which is in this case 5 volt, VO by 5 volt. That will be common mode gain when the common mode input is 5 volt. You can do this again for when V1 is say 15 volt, V2 is 15 volt. Find Kc, which will be VO at that point when both these are at 15 volt divided by 15 volt. That will give you some Kc. All this should ideally be 0 because this should be a difference amplifier, but may not be. So find out if this is not 0, then the amplifier is not good. But if it is close to 0, then the amplifier is good. So this is about, so this is, this entire thing that we have talked about is DC common mode gain. Because the two inputs are 5 volt and DC, that means constant, they are not varying with time, or 15 volt, but they are not varying with time. Next we are going to talk about what happens when the inputs are AC. Okay, suppose okay, when inputs are AC, a new problem arises. Okay, and this is due to non-identical op-amps. So this is our circuit. Suppose these two op-amps are not identical, and the input here is varying, it's an AC, the input here is varying, this is an AC. So therefore the output here will also vary, that will be AC, this output will also vary, that will also be AC. But we have talked in experiment number 7 about the slew rate, which says that the output does not change instantaneously if the input is changed. So if in an op-amp, suppose I have this terminal grounded, one terminal grounded, minus terminal, the plus terminal has a voltage supply which changes like this, minus to plus, then the output here should also change instantaneously at this instant. If this is t equal to 0, this is t equal to 0, ideally the output should go from minus to plus like this. But practically the output goes like this. This time interval although is very small, and this rate of change of voltage we call it a slew rate, but it takes some time. Okay, but there is a delay, right? So there is a delay, and this delay, the amount of delay can vary from op-amp to op-amp. So this op-amp and this op-amp might not have same slew rate. They might not have same slew rate. Okay, so the rate of change of the output here and the rate of change of this output may be different. Okay, so let me just draw the stage 1 once again. The stage 1 is like this. Okay, so this is minus, plus, minus, plus. Feedback always at the negative input. Okay, negative feedback. So that's stage 1. Now if I have an input here which is like this, varying sinusoidally, this will also cause the output here to vary. So here also the input, if you think about it, you'll find out that here also the output varies sinusoidally. Okay, so let me draw it here. Let this be, this curve be the input Vi1. Here the output will also vary sinusoidally, but will have a delay because of this, because it cannot change so fast. So it will delay slightly. It will delay slightly. So this will be the output. Okay. But at low frequency, this is not that much visible, almost, because it's varying slowly. So output can follow it almost in a same way. But if I have high frequency like this is the input. Now the same amount of delay here, okay, so same amount of delay I take here, so that will be like this. So here if this is equivalent to maybe, I don't know, if this is only about 10 degree, here when the frequency is high, this can look like 30 degree possibly, this angle. So there will be a delay. And here as well, if I have this is also varying sinusoidally. Suppose what I do is this, I sort this, I give common voltage which is varying sinusoidally, okay, at this point. So here also the voltage will vary. So this, let this be the input. Here also it will vary sinusoidally but with a delay, and this delay will be different. Maybe this delay is more. I have drawn it actually quite a lot, but okay, maybe this is the case. This delay and this delay are different. Therefore, what happens? The difference between this and this, so this is VO1, this is VO2, so the difference, so this is VO1, this is VO2, okay. So if you just take the difference, you will find that, yeah, there is some difference. Like here, this is positive, this is, so there you'll find some difference with the same frequency. But had there been no delay, so if let this be the input, here also the same input, had there been no delay, the output here will just follow the same pattern. Magnitude can be different, of course. Here also the output will be same. And if you take this difference, so this is VO1 minus VO2, here if you take this, so this is VO2, this is VO1, that will be 0. This is VO1 minus VO2, that will just be 0. If these two op amps were identical, their delays were identical. If not, you see, there is some voltage. And particularly as frequency increases, okay, so then this delays also become more prominent and this voltage appears. But at low frequency, here, say at low frequency, here if I have like this, if I have a slightly higher delay, so these two are not same, but if you take the difference between this is VO1, this is VO2, you'll find, just do it yourself, do this difference, compute this, you'll find, okay, there is some voltage gap, maybe like this, but with a smaller magnitude. Maybe this is true at very low frequency, because at very low frequency the output if this is almost DC, output follows the input quite well, so you'll have very less difference between these two voltages. But at high frequency this will be a problem. Maybe at some frequency this can be prominent. And maybe then if you increase the frequency further, maybe it's possible that these two delays become equal again. Okay? Think of it, these two delays may become equal again. So depending on the frequency, this voltage which was supposed to be 0, this should be 0, this common mode gain should be 0, but this can be non-zero, depending on different frequencies in case of AC. And therefore, for AC, at different frequencies you can have different common mode gain. What it is actually, I mean, common mode gain should be 0. I mean, if I just listen to this, this is interesting. If I give same voltage here, okay, slowly varying voltage, if the same voltage is here, ideally I should have same voltage here between these 2 points. So the difference between them should be 0. But if these voltages are varying fast, then these 2 voltages are not able to follow this quite at the same speed, and therefore there will be a difference between these 2, and they will not be at the same voltage. Although this is at the same voltage, this will not be at the same voltage, and then when this is fed to the second stage, that will be amplified again. So although the inputs are at same voltage, output will not be 0. So therefore you have to find out this common mode gain in lab at different frequencies, and then you have to plot a function where you have frequency along the x-axis and CMRR or common mode gain along the y-axis, and see how does that look like. Generally in previous years we have found out that this common mode rejection ratio, it increases and then decreases again. Ideally this should be in log domain. If it is in log domain or in decibel, this should be minus infinite. Okay, CMRR should be 0, so log of that should be minus infinite, but we find it increasing and decreasing, so that you have to do. What you have to do, you have to sort these 2 terminals here in this circuit. Okay, you have to sort these 2 terminals and give some input sinusoidally varying, not 0. Change the frequency and look at the output. The output ideally should be 0 because it should be ideally a difference amplifier, but you will still find some output AC, same frequency as this. So find out the power of this divided by power of that, take the log, that will be the CMRR, common mode rejection ratio, and plot it. So this is what you have to do also in the lab. Thank you. This had been quite a long video, I guess. Thanks for your patience. Thank you. Have fun with experiments.